Hello everyone, and welcome back to this Nanophotonics and Plasmonics course. In this video, we're gonna discuss the topic of nonlinear plasmonics, which is just an extension of the field of nonlinear optics. So first of all, it's important to notice that noble metals that we've discussed in this course, like gold and silver, which are plasmonic metals, they exhibit extremely large optical nonlinearities. As an example, for instance, the third order nonlinear susceptibility, which we're going to discuss later on for a metal like gold, is more than 2 orders of magnitude larger than typical susceptibilities of nonlinear crystals. And that's basically including, for instance, lithium niobate. So this is extremely interesting. So typically, when you excite a metal with optical excitations, you basically couple light with those free electrons from the conduction band, and you generate those localized surface plasmon resonances. And this is what we've been doing for the past several weeks now. And as a result, because you excite those plasmons, then basically you're going to generate very strong localized electromagnetic fields at the vicinity of the metallic nanostructure. And that basically gonna allow to really enhance very weak nonlinear processes, and therefore that's basically gonna be very dependent on how those fields gonna be around the nanoparticles. So that's why plasmonic nanoparticles exhibit also very strong nonlinearities. So in addition, just to provide enhancement of nonlinear effect, is also going to increase, of course, the response time to the optical excitation, because nonlinear effects are usually very fast. And basically, one of the main aspects of using plasmonic nanostructures is that it's going to allow to obtain nonlinear optical components at a nanoscale. So this is also extremely valuable for applications. Those nonlinear effects, they are really dependent on the material symmetry. When I talk about material symmetry, I'm really talking about the atomic crystallographic structure. So while most of the materials, they actually exhibit all third order effects, second order effects are really just possible only for non-central symmetric materials. So the central symmetry is really a crystallographic properties, a crystallographic symmetry that has basically an inversion symmetry point. So for metals such as gold and silver, which have FCC crystallographic structures, they are central symmetric. So by default, gold and silver will not exhibit second order effect. We see that it's not entirely true, and we can actually go around this central symmetry condition. This is true for dipole approximations, and we're going to see that we can also go around this limitation as well. How do we go around those limitations? So if you use quadrupoles, for instance, or magnetic effect, that's going to allow to actually enhance or actually allow and activate those nonlinear second order effects. So the use of quadrupoles and iodo modes, magnetic effects, can allow you to go around this dipole approximation limit for second order effect. So these are just a couple of examples of nonlinear optical processes. So these two second harmonic generations, which is also known as hyperrelay scattering by the chemist, or sub-frequency generations, or second order optical effect. We're going to discuss second harmonic generation a little bit later. Some examples of third order effects, like the third harmonic generation, 2-photon excitation processes like 2-photon excited luminescence or 2-photon absorption spectroscopy, optical Kerr effect, 4-wave mixing, or coherent Raman scattering. These are third order processes that can occur as a result of high nonlinear effect in the materials. So nonlinear plasmonics is a fairly widely unexplored territory. This is still a growing field. There's more and more work done every day, whether if it's developing new techniques, new experiments, discovering new effects and new mechanisms, but overall it's still fairly unexplored as opposed to just regular linear optical effects. And some of the effects that have been studied so far are second harmonic generation, third harmonic generation, two photon luminescence, and four-wave mixing. So we're going to discuss only the second harmonic generation later on, because that's the most popular nonlinear effect which is being studied in plasmonics. Those nonlinear effects, they basically start arising when you have a very strong electromagnetic field that's basically now going to excite these materials. And as a result of the presence of this very strong electromagnetic field, then the electrons of the system will basically deviate from this ideal harmonic motion that we've been dealing with for instance in the Drude Sommerfeld model. And basically you need to have an expansion of this unharmonicity in the form of a power series as a function of the field strength. And that's basically going to result in a mixing of incident fields. And that's going to basically lead to the production of new electromagnetic fields that are basically now providing resonances and oscillations of those electrons at frequencies that are basically just the sums or the differences of the different incident frequencies. So these are just three examples of such processes. So as I mentioned, the second harmonic generation is basically one of the key process. So what happens is that basically now you're able to excite the electrons in the system basically by just having two photons of the same frequency that are being absorbed at the same time. So now it's basically a two photon process instead of just exciting with one photon. Now you basically have two photons that are basically absorbed at the same time to excite the electrons in the system. And when the system is going to basically relax, it's going to basically start emitting light at a frequency of 2 omega, so twice the frequency that is being used to excite the system. So that's why you have this second harmonic generation. So you're doubling the frequency or doubling the energy. So this is a very straightforward process which has been studied for a long time already. You have more complex schemes like this four-wave mixing that I've mentioned before. So this is of course a third order process that, as I discussed, is basically absorbing two photons with different frequencies. It could be the same, but you basically absorb two photons simultaneously, and then you have emission of two different photons with two different energies. They could also be the same eventually. So this is basically a four-wave mixing because you have four photons being evolved. But this is a third order process, so this is going to be dependent on the susceptibility of third order. And then you have more complex processes like the coherent anti-Stokes Raman scattering, where you have photon in, photon out that are happening with different frequencies, and this they can become a very complex system and very complex physics. We will not discuss that, but this is just to give you an idea about what's happening, that you're mixing up different fields or different photons with different frequencies, and then basically what you're getting out as optical response from the material is something with a different frequency, which is either the sum or the difference of what has been used for the excitation. So mathematically, what happens? So we've seen basically since chapter 2 that the response of a material to an optical field, in a particular case an electric field, is described by the material's polarization field P. So we've seen that this polarization, the macroscopic polarization from material, so far was basically just proportional to the electric field. So far we've been dealing with this first term, so that's the first order, or that's the linear response. So when we talk about linear response theory, when we talk about Drude models, we are just looking at this first order. So the polarization of the material is just proportional to the incident electric field. Now, as a result of these nonlinearities, we have to also account for the fact that the material can actually be proportional to the square of the electric field, or basically the electric field intensity as opposed to the electric field strength, or proportional to the third order of the electric field or the fourth order, and so on and so forth. So ideally we have an infinite series, that's an infinite power series in the field strength. So of course practically the higher the order, the weaker the effect. So most of the materials that we are looking at basically can have first, second or third order optical response. So this susceptibility, so you have a susceptibility for the first order, which is different from the susceptibility for the second order and the third order. So of course the actual value of those susceptibilities is decreasing with basically the order. So that's basically what we have. So this is the electric susceptibility of the material, and when you have basically strong field, you need to account for those higher order terms. Now for the case of plasmonic materials, that's exactly what we just discussed. Even though those terms might be small, because we have very strong localized electric fields around the particle, basically you're enhancing those terms. You're enhancing the polarization because you have very large electric fields. So large electric fields, basically to the power 2, 3, or 4, you see that you can have very large contributions. So of course it's going to be weighted by the actual value of the electric susceptibility. So just briefly on two examples. The first one is just the optical Kerr effect. So the dielectric permittivity of the material, if you include the optical Kerr effect, is composed by basically the first order response, the linear response, and then it's basically it's a third order term. So this is the optical Kerr effect, which is basically a third order term, and is proportional actually in that case to the square of the magnitude of the electric field. So you see that in that case there's no second order, and that's basically what is used to describe the optical Kerr effect in materials. The other example, to go back to this well-known second harmonic generation, so if we look at what's the actual value or expression for this second order electric susceptibility, the first thing to notice is that this is frequency dependent. It's not just a constant. You see that basically it depends also on the linear term, and it's weighted by this additional factor, which you can see that we have the plasmon frequency of the material. So this is basically describing the second order electric susceptibility of a plasmonic material. So it's frequency dependent, and it's, of course, it's materials dependent through both the carrier density here on the conduction band, on the plasmon frequency, and of course on the linear electric susceptibility as well. And those basically models for those different effects can basically be used in also computational modeling. So you can input that in FDTD or in FEM, DDA, whatever, and calculate the nonlinear optical response of any plasmonic structure. So you can calculate the field, you can calculate the charge, the radiation pattern for those nonlinear terms. So you can study them the exact same way. It's just that now, instead of having just a dielectric permittivity or a linear electric susceptibility, you also need to include those higher order terms to describe the material's response. So nonlinear response of plasmonic structures can be actually probed experimentally using various optical microscopy techniques and spectroscopy techniques. So you can actually obtain confocal images. So this is an example for those gold nanorods that are about 100 nanometers in size. They are forming those nice antennas, and they have done basically confocal optical microscopy on those guys to image the different nonlinear processes that are shown here. So second harmonic generation, 2-photon luminescence, and 4-wave mixing. Something which is worth noticing is that those different optical processes, they are basically proportional to either the second order or third order electric susceptibility, but also just only the real part or the imaginary part of those susceptibility. So it's in fact, if you're able to image those processes, it's pretty much like imaging the imaginary part of the third order susceptibility or the second order susceptibility, or the real part of the third order susceptibility. So you have a direct measurement of those fundamental properties of the material. So something which is also important to notice is that, of course, those optical processes, they're going to be very strongly dependent on the actual geometry. And basically, for instance, it's going to be also very dependent on the gap and distances And the reason why is because we've seen that those things are really strongly dependent on the electric field. If you have a gap in the dimer, for instance, you're gonna really change the amount of electric field in the gap when you change the gap distance, and therefore you're gonna strongly impact the amount of polarization you're gonna generate from those nonlinear effects. So this is just a simple example of two gold nanoparticles of 60 nanometers in diameter each, and I've done this study for this the particular case. This is a 4-wave mixing signal, so third order nonlinear process, and they have studied how much 4-wave mixing signal they get as a function of the distance between the two nanoparticles. So when they go from large separations, when nanoparticles are fairly well separated, all the way to nearly touching nanoparticles, see that in that case you're half a nanometer of distance, there's basically a 4-order increase in terms of intensity for the 4-wave mixing. So because you go from 14 nanometers of separation to 0.5 nanometer of separation, you have a drastic increase in terms of field intensity inside the gap. And because you're looking at e to the third, then when you increase the electric field in the gap, you're gonna basically increase the 4-wave mixing to the third power, and then basically that's basically gonna give rise to very strong increase in this nonlinear optical process. Let's just focus for a second on a particular case of signal harmonic generation. I won't discuss necessarily too much about that. I just want to highlight a couple of things. So first of all, the first thing to notice is that because of the central symmetry of gold and silver in general, and central symmetry also of the shape of the nanoparticles that are being fabricated, the second harmonic generation is normally forbidden. So you cannot have, if you just consider the symmetry of the material, you cannot have second harmonic generation. You don't have any second order optical process. This is in the electric dipole approximation. However, we know that we do observe second harmonic generation from plasmonic nanostructures, and this is simply because we have higher order modes that are actually at play. So like quadrupoles, octupoles, and so on and so forth. So they must be involved in the description of second harmonic generation in plasmonic nanostructures. So we need to account for those higher order modes. So central symmetry forbids second harmonic generation, and that's why we cannot have second harmonic generation in small nanoparticles. But if you take large nanoparticles that sustain high order modes, you can actually obtain second harmonic generation from those systems. So just to give you a quick flavor about what's happening, so if you have only a dipole plasmon, so basically this E1 mode, you will not be able to obtain second harmonic generation, so you cannot obtain any nonlinear effect. But because we have quadrupoles, those basically dipoles that you have in the system, gonna mix with the quadrupoles as well. So there's gonna be a mixture of modes. Those modes gonna start mixing together, and that's basically gonna give rise to another dipole, which gonna be in that case in the transverse direction, with basically a frequency which is gonna be double of that of the incident electric field. So you're gonna basically obtain nonlinear effect because you have these quadrupoles that will be mixing up with the dipoles that you're also exciting in the system. So you have this mixture of modes that is necessary for the generation of second harmonics. So plasmonic structures, as I said, are very valuable for nonlinear optics because they are basically first well controlled in terms of fabrication process. You can really control the type of design you want, the size, the composition at the nanoscale. So they are very valuable for obtaining nonlinear processes, nonlinear optical effect at the nanoscale. So as I said, this is a fairly new field. This review that some of you may have seen already is basically from 2012. So now it's starting to age a little bit as there's more and more work done on that, but there's still way more to do in terms of designing new optical experimental setups to actually probe those effects, because these are very weak effects overall anyway, and they are very small nanoparticles, so the amount of signal can be also weak, and some effects are actually very complicated to generate and observe and measure. So there's a lot of things that need to be done. So this concludes basically this chapter. So it was a very quick one, but I wanted just to provide a very quick overview of the concept of nonlinear plasmonics and show you that not everything is just proportional to the electric field, but now we have also in some cases the contribution of the square of the electric field or the cube of the electric field, and this is because you have nonlinear response of the material that need to be included, and this is true when you have very strong electromagnetic fields that are at play, and basically you need this nonlinear susceptibility with higher orders in order to describe those effects. Nonlinear plasmonics, as I said, is still very young field, so there's a need for new techniques, new structures as well, so designing new structures that are more efficient at generating those nonlinear effects. There's of course a need for theoretical models as well. Not every chi can be actually described from a theoretical model. Sometimes it's more empirical than anything, so there's a need for developing new models. And basically plasmonics is very suitable for a lot of applications due to the fact that you can actually scale down things in size. It's also ultra fast. You're looking at plasmon resonances that are operating at the femtosecond time scale, so this is very fast optics, and it's a way basically just to reduce the optical power, since you're basically enhancing the nonlinear effect.